Hello, my name is Lorenzo Corrêa, and in this speech I'll present the results and discussion regarding the mathematical model of a thermomagnetic motor. This work was developed by me and co-authors, supervised by the Professor Paulo Trevizoli at the Laboratory for Emerging Thermal Systems at the Federal University of Minas Gerais. The global energy demand is currently increasing. According to the World Energy Council, using more efficient energy conversion systems is a way to supply the increasing demand without increasing the energy production. One means to do that is to recover heat wasted through industrial process and convert it to a more useful type of energy, such as mechanical or electrical. The waste of heat can be divided according to its temperature. High grade corresponds to temperatures higher than 650 degrees. Medium grade are from ranges from 230 to 650 degrees, and low grade are for temperature lower than 230 degrees. However, recovering low grade heat waste is a low efficiency process and mostly made from solid state thermal energy harvesters. Among those, thermomagnetic motors and generators can be applied as thermal energy harvesters. In this figure, we can show how a thermomagnetic motor operates. In this case, we use the spring force to balance the magnetic force. Initially, in figure A, the magnetic material is placed in a low field region and it's cooled down by a cold fluid stream from the cold reservoir. When the magnetic material achieves a temperature lower than its current temperature, it reaches a ferromagnetic phase and the magnetic material is attracted to the high field region as shown in figure B. The displacement of the magnetic material only happens if the magnetic force is higher than the spring elastic force. At this point in figure C, the magnetic material is heated by a hot fluid stream from a hot reservoir, which could be supplied from a low-grade heat waste. And then, when the magnetic material achieves a temperature higher than its current temperature, and therefore a non-magnetic phase, and the magnetic force is lower than the spring elastic force, the magnetic material is moved back to the low field region as shown in figure D, restarting the cycle. This way, it becomes possible to convert heat into mechanical work. So, the main objective of the present research is to develop a mathematical model for the heat transfer and thermomagnetic phenomena of a motor to simulate a thermomagnetic cycle. To accomplish this objective, a few considerations were made. So, gadolinium was chosen as the magnetic material. A mixture of water and ethylene glycol with 80 to 20% ratio is used as a heat transfer fluid, and gadolinium is structured as a porous media to increase the heat transfer rate due to a large heat transfer area. The magnetic field is generated by a nested Halbach cylinder composed of three concentric cylinders as shown in the figure on the left, and the field is generated inside in the green region. The figure on the right shows the magnetic field over the position inside the cylinder. The position X is in a direction parallel to the cylinder axis. The equation below represents a numerical approximation that generates the value of the magnetic field for any position, considering that 0 is the center of the cylinder. To model the heat transfer inside the motor, the one-dimensional condition was chosen to simplify the system, the one-dimensional heat transfer condition. The fluid and the solid phases interact within the porous media, so their equations are coupled, and no actual heat transfer was considered within the solid phase. This way, the fluid energy equation stands as this first equation shown here, with the first item being related to the change of energy inside a volume in time, and the second is related to the energy that crosses the volume borders. The third represents the convection heat exchange with the solid phase, and thus this justified the coupled equations. The fourth represents the advection and diffusion of the heat within the fluid, and the fifth is the heat generated by the viscous friction. As the axial heat transfer wasn't considered in the solid phase, the solid energy equation presents that the change in a solid volume is only related to the change in energy is only related to the convection with the fluid for that volume. And the last equation here is Ergun's equation for the viscous friction in a porous media. For the modeling of the positioning inside the motor, kinetical factors were disconsidered. This way, the chosen way to evaluate the position in time was to establish equilibrium between the magnetic and elastic forces. The magnetic and elastic forces can be described by these two equations here, so both of which are correlated with the position of the heat exchanger. During the heating process, in the beginning, the magnetic force is strong and holds the material in the high field region. As the material heats, the magnetic forces diminishes and the elastic forces overcomes it, allowing for movement. The movement used in the model moves the material 1 millimeter in the direction to the lower field and recalculates both forces. If the equilibrium is not reestablished, the movement continues until the equilibrium is reestablished. During the cooling process, the movement is the same, but it starts when the magnetic force overcomes the elastic force as opposed to the heating process. And the movement also goes in the opposite direction as the material has to go to the higher field region. The system was numerically implemented with use of the Python programming language. The finite volume method was chosen to allow the numerical integrations of the energy equations. The advective and diffusive terms for the fourth term of the energy equation in the fluid could be evaluated using the weighted upstream differentiation scheme, and the following equation is a result of this numerical implementation. As it can be seen, the temperature for each volume depends only on the temperature to the volumes that surrounds it. So the volume immediate before and after, and its own temperature on the last time step for the finite volume method. As each volume temperature depends only on 3 temperatures of the complete mesh, the system is a 3-diagonal and the 3-diagonal matrix algorithm was used to solve it. 2 boundary conditions were applied of mass inlet with fixed temperature for the first volume, and this temperature depends on whether it's a heating process or cooling process, being respectively 40 degrees and 0 degrees Celsius, and only advective mass outlet condition for the last volume. For each time step, the convergence condition states that the sum of difference of temperatures for each volume between the last and the prior iteration must not exceed 0.0001 Kelvin, and for a cycle, the sum of differences for each volume in each time step must not exceed 0.1 Kelvin. A 1000 volumes mesh was used with time steps of 0.001 second as the mesh in time. The performance metrics for the system were 5 as follows. Load loss calculated by using the Ergun's equation. Total produced power calculated using the maximum and minimum spring stored energy that over time, so it becomes work over time to become power. Pump power calculated using the load loss. The net power, which is the difference between the total power and the pump power, and the backwork ratio which is the ratio between the pump power and the total power. Two simulations were made using the following parameters, and the three different parameters that can be outlined between these two simulations were the elastic constant, the heat exchanger length, and the mass flow rate. Here we have the results of position over time for both cases. In the upper figures, we have the whole simulation position, which is composed of a first cycle with predetermined time to establish start and end of the movement of the heat exchanger. Then the cycles are repeated until the system reaches a periodically developed state. The lower figures show the position over time for the convergent cycle in the periodically developed state. As it can be seen, in the first case, the cycle is much longer, being close to 0.7 seconds, as opposed to the second case of approximately 0.4 seconds. And here we have the performance metrics calculated for both simulations. Despite having a greater period, the case 1 presented a greater produced power, which can be explained both by the greater length, which leads to higher magnetic forces, and the greater elastic constant. The pump power is almost the same for both cases. It depends on the length and the flow rate. Therefore, the rise in flow rate for the case 2 compensated for the lower length. Thus, the net power and the backwork ratio were better in the first case, since the pump power was almost the same and the produced power was higher. So the higher magnetic forces were more relevant to improve the performance metrics comparing both cases than the shorter cycle presented in case 2. The model was successfully implemented, allowing the analysis of the pump power and produced power and derived results of net power and backwork ratio. The position of the heat exchanger during the cycle provided important information for the simulation. Therefore, other ways to define the start and end positions of the heat exchanger could improve cycle performance. Also, the low backwork ratio values found point towards the viability of the system, given that the pump power required was much lower than the generated power. This way, the thermal waste could be diminished. We would like to thank the Department of Mechanical Engineering from UFMG, especially though the Pró-Reitoria de Pesquisa, and CNPq for supporting this research with an ADRC scholarship. Here are some references used in this presentation. Here are some more, and thank you for your time.